Hello students, in the last session we completed sums that were related to kinetic potential and then the total energy. So all those pattern sums were completed, and same way we did see sums that are related to vertical circular motion of a bob. Okay, we started solving those kind of sums and we did around like 5 to 6 sums regarding that vertical circular motion of a bob. So in this session we will do rest all other sums that are related to that concept, and then we will start doing sums that are directed towards the spring and then the force balance of the spring, and all those sums will be done. Fine. So in this session we will do around like 10 to 11 sums. Got it? Fine. So let's jump into it. So let's see the 35th question. So altogether we have completed 34 questions so far. So now let's see the 35th question, which is like, as shown in the figure, a mass is performing vertical circular motion. Okay, so there is a mass that is undergoing vertical circular motion. So the same understanding and the concept. The average velocity of the particle is increased, then at which point will the string break? Okay, so they're asking us to find the velocity is keep on increasing, so at which point the string, the possibility of the string to break will be at maximum at which point. That's what I need to find over here. So this is kind of same situation we have already seen in the last class. Okay, so the string will break at its at its lowest position, right? So that will be the point where it'll have the maximum tension. So at point B the string will break. The answer over here is like option 2. Simple question, the same exact question similar to that of something that we have seen in the previous classes. Okay, so here the answer is like option 2, which is like B. Fine. So it should be clear, you shouldn't have any doubt. Let's see the next one. This sum is based on the concept of spring. Let's see what the sum is. Two blocks, capital A and capital B, of masses 3m and m respectively, are connected by a massless and inextensible string. Okay, so you are having a string that is going to connect like this 3m mass and then the m mass. So you are having string over here, it is not spring. Fine. So above this mass A, it is getting connected by a spring. Fine. The whole system is suspended by a massless spring as shown in the figure. So you have got like a thread over here and then a spring that is connecting this entire system. Fine. So they have given the figure clearly as shown in the figure. What they are asking us to find is the magnitude of acceleration capital A of A and B immediately after the string is cut. Okay, so if I cut this string, what will be the acceleration of this 3m mass and this m mass? That's what I need to find. Okay, if I cut this string, it is pretty obvious that capital B mass will experience a force equal to that of the gravitational force. Okay, therefore it will experience the acceleration that is equal to that of G. Okay, so with the case of this mass B, that is not a problem. So that is like a straight away thing that we could actually take it easily. So this will fall down like a free fall, therefore acceleration of this mass will be like G. So that stuff is done. Got it? So that's a simple case. But once you cut this spring, what will happen? Once you cut this string, what will happen to the mass 3m is it will actually start oscillating, because initially this was balancing, the spring was actually balancing 4m mass. Once the mass m is cut, you will have a spring force that will be equal to that of the 4m. But with the case of the mass, it is just only the 3m. Okay, so after the string is cut, you have got like 3 mg that is acting downwards. So you will have like 3 mg that will be acting downwards. Initially, when this was a complete setup, you have got like 4 mg that was acting downwards, right? But once the string is cut, only 3m mass is over there, therefore it is just going to balance 3 mg. But where in the case of spring force, it has actually stretched extra because of the extra mass over there, right? Therefore, with the case of the spring, you are going to have a spring force Fs, which will be equal to 4 mg. Got it? So now I'm just ready to find the acceleration of this mass A, because I have found out the forces over here. Okay, so when I know the force, obviously I'll be able to do the force balance and I'll be able to get the acceleration, right? Okay, so simple, straightforward. Just do the force balance thing, free body diagram, you will end up getting the answer. So over here you will have like 3 mg that will be acting downwards, so you will have like 3 mg that will be acting minus j cap. Same way you will have plus 4 mg that will be acting like plus j cap. One will be like acting downwards and the other one will be like acting upwards, which will be equal to the acceleration produced with the case of the mass A. Okay, so that will be 3m mass is over there, and I will have to find out that acceleration A. Okay, so in this situation you will have, if I do the subtraction, you will have like mg that will be acting upwards j cap, which will be equal to 3m times A. So in this situation, these two stuff will get cancelled out, m will get cancelled out. Therefore, acceleration A at that instant will be equal to that of g by 3. So A will be equal to g by 3. Okay, so in this case, it is pretty obvious. You will have the acceleration initially to be in the upward direction, which will compress the spring, and then it will start oscillating up and down. Okay, so here, as the spring force was greater when compared to that of this gravitational force, therefore this mass will just move upwards, then it will do the oscillation. The acceleration at that instant will be equal to g by 3. Therefore, I'm ready to mark the answer over here. So what they're asking is to find is in this order the acceleration of A and then the B. Okay, so the acceleration of A will be equal to g by 3 and then the acceleration of B will be equal to g. Therefore, option 1 will be the answer over here, right? So the answer over here is like option 1. Okay, you should be clear with this sum, simple sum. Okay, a little bit of tweaking to it will end up getting the answer. You shouldn't have any doubt in this question. Let's move on to the next one. This sum is also based on springs. So from now onwards, you'll get questions mainly related to springs. Okay, so this session we will mainly do sums that are oriented towards the spring. Okay, so let me read the question. You have got like two similar springs P and Q having spring constants Kp and Kq. Okay, so we have got like two spring constant Kp and Kq for two different springs. Fine, such that Kp is greater than Kq, which means the spring constant of the P spring is greater when compared to the spring constant of the Q. Fine. So you have got like two springs. Then what they are telling you is they are stretched first by the same amount, which means in the first case, I'm just going to stretch it to the same amount of displacement with the case of both the springs. Then for the second case, then by the same amount of force. So in the first situation, the distance was same, x was like same. In the second case, the force that I gave to stretch it was like same, which means now, in the second situation, the displacement would have been something different, okay? The distance that got stretched would have been different, but the force that I gave to that spring was like same. While drawing the diagram, you'll get it pretty more clearly. Okay, so the next statement is the work done by the spring WP and WQ are related as in case A and case B respectively. So what I need to find over here is how does the work actually is getting stored into the spring. That's what I need to find. In what fashion it is getting stored in case A and case B respectively, which means when you look at the options, they're asking us in what case it was greater. With the case of spring Q, was it greater, or with the case of spring P, it was greater? That's what I need to find for like two different scenarios, right? So first, let me take the case A and I'll do this solving. Same way, we'll have to do it for the case B, okay? So the first one is like for the case A. So for case A, that will be the first solving, and then we'll do it for the case B, okay? So with the case of A, you have got two different spring. Got it? So you have got like two different spring. Yeah, so here I have just stretched this spring from its mean position. Let us take this to be my mean position. So from mean position, I have just stretched it to a distance of x. So with the case of both the masses, the displacement was same. So that's the case that they've given over here by the same amount, which means the x displacement was same with the case of both those masses. Fine. So if that was the case, in which spring I have done more amount of work, that's what I need to get. So let me use the formula for the work stored into the spring, which will be like potential energy U, that will be equal to half kx square, right? So I'll use that formula. So it doesn't matter whether you're going to put W or U, it simply means energy is getting stored into that spring. Whether you do the expansion or you do the compression, in both those situations, energy will only be stored in it. Therefore, here WP, which is nothing but the potential energy over here. So WP will be equal to half, okay, KP, and then you'll have the x square. In both those situations, I've just stretched it to the same amount, right? So then for the spring Q, you'll have like WQ, which will be equal to half, okay, so KQ x square, right? As I have stretched to the same amount, x is going to be constant, therefore those two stuff I'll be able to cancel it out. Same way, half will get cancelled out. Only thing that I'm left over here is like Kp divided by Kq, right? So when you look into this one, so they have given it clearly Kp is greater than Kq, which means this value, this entire term has to be greater than 1. Okay, so Kp has to be greater than Kq. So when you look at the left hand side and right hand side, obviously this entire term is greater than 1, and then Kp is in the numerator. Therefore, work done in the spring P is going to be greater when compared to the work done in the spring Q. Therefore, with the case of the first situation, you have like Wp that should be greater than the Wq. Okay, so this thing has to be obvious. By the way, when you have like greater spring constant, I'll have to give greater amount of force to produce the same amount of displacement. That's the thinking that you need to know, right? This part should be clear. Same way I'll do it for the second case. That too will be a kind of similar solving only. So with the case of the second case B, you will have two spring that got stretched by the same amount of force. Okay, so yeah, so in this situation it will have like different displacement, but it will have like the same amount of force that is acting over that particular block. Okay, so in this case you have F spring given by me was like constant. Okay, so whatever force that I gave, same amount of force will be produced in the spring in the opposite direction, right? So I'll have to do a little bit tweaking to this formula W, and then I'll be able to do it. So let me do the tweaking to it. So you have like U that will be equal to half k x squared. In this case, I do not know the displacement x over there. I'll have to find the relation between the k. Okay, I do not know the displacement. Only thing that I know is in both those situations, force was like same. X is obviously going to be different. So I'll have to relate it with the force. Okay, so spring force produced will be equal to that of kx. Fine. I do not want to worry about the signs over there. Only thing that I'm concerned is with the magnitude. Okay. So kx, right? So I'll have to replace this one. So if I have to replace this one, I'll just divide it by k, and then in the numerator you'll have like k square x square, which will give you like fs square. Okay, spring force the whole square. Therefore, the formula that I need over here is half, okay, force given by the spring, which will be like fs square. That was the force that I gave to that block also, divided by k. Okay, so this is the formula with which I need to do the ratios. So if I have to do the ratios, you will have like Wp divided by Wq, which will be equal to half, okay, Fs square divided by Kp divided by half Fs square divided by Kq. Okay, so if you solve this one, you will have half, it will get cancelled. Same way fs square will get cancelled out. Then you will just be left with kq divided by kp. So now it got flipped, and then this term is actually less than 1. Therefore, the answer that I'll get over here is actually opposite to that of this one. Okay, because here it is inversely related. It is oppositely related when compared to this one. Here you have got like kp by kq. In this situation, you will get like kq divided by kp, right? Therefore, the work done will be stored in this case in this fashion, such that you will have WQ that will be greater when compared to WP. Okay, fine. So by now you should be able to understand this by intuition. So with the case A, the displacement was same. So x wasn't a parameter that was determining the work. Displacement wasn't the parameter, because in both those situations displacement was same. So depending on the k, the force was acting. Therefore, more the k, more the work I needed. Therefore, in the case A, WB was greater than WQ. Okay. In the B case, you have got like same amount of force. Okay. So when you have got like same amount of force, the spring that was easier to stretch got stretched to maximum distance when compared to the spring that was hard to stretch. Okay. So you have got like more displacement produced over there. Therefore, in this case B, WQ was greater than the WP. Okay, so that's the intuition and thinking logic behind it, which you need to know. Okay, so I'm just done with the relation. Therefore, now I'm ready to mark the option. So for the first one, WP should be greater than WQ, and for the second one, WQ has to be greater than the WP. The answer over here is like option 1. Fine. You shouldn't have any doubt in this question. It should be easy and clear. Let's move on to the next one. Next question that we are going to see is, a block of mass capital M is attached to the lower end of a vertical spring. Okay, so you have got a spring, and to the lower end, a mass capital M is attached. Fine. The spring is hung from a ceiling and has force constant K. So the spring constant is like K, and it is hung from the ceiling. Okay. The mass is released from rest with spring initially unstretched. Okay, so that's the key idea that you need to know. So here I'm just going to release it such that I'm holding the mass in my hand and I'm just going to release it. So in the initial situation, the spring was unstretched. So spring didn't balance the force of mg. Okay, fine. So while drawing the diagram, you'll understand it pretty more clearly. Then you have got the maximum extension produced in the length of the spring will be. So what will be the maximum extension that would have been produced with respect to the length of the spring? That's what I need to get, right? So let me draw the initial condition diagram. So you have got a spring which is attached to the ceiling. Okay, and there is a mass m that is attached to it. Okay, so this is the initial setup. So this will be mass m, which is like capital M. Okay, so we have got capital M mass that got attached to the spring. Okay, so initially I'm just holding it with my hand. Fine, so I'm just holding this mass capital M with my hand. So in this situation, there was mg that was acting downwards, which was balanced by my hand. Okay, so in this case, there was actually mg that was acting downwards. Okay, this mg was balanced by the force given by my hand. Okay, so in the next case, what I'm going to do is I'm just going to release it. So as soon as I release it, so in this situation, obviously the force in the spring was equal to 0. Upward force in the spring was equal to 0, right? Then what I did is I just released it. So when I released it, there was an extension that was produced, obviously, because mg will be dominating. There wasn't any spring force acting upwards. So because of that, the spring will start to stretch and then it will oscillate to and fro. What they're asking us to find is not the mean position where it is going to come to rest. They're asking us to find the maximum extension produced in this case, right? So the mean position will be something of this sort. So once I release this, once I take my hand, what will happen is there will be this extension produced in the spring. Okay, so because of this extension, there will come a point where this mg, okay, so this mg will be balanced by the spring force fs. Okay, so fs will be equal to mg. So there will come a point where mg of the mass will be balanced by the spring force fs. Okay, so I just released it. So what has happened over here is the spring started to stretch and the mass mg started falling downwards. So the spring is going to stretch, which will produce an opposite spring force. Okay, so mg and mg will get balanced, but in this situation the mass still has kinetic energy into it because it was falling downwards, therefore it was generating velocity into it. So because of that velocity, after producing this extension, so that the force got balanced, still it will produce extra more extension to it. Okay, so it will still move downwards because you are having kinetic energy in the situation. So obviously it has some velocity into it, right? So as it is having certain velocity into it, there will be much more extension produced to it. Okay, so here it will not stop in this mean position, it will further undergo extension into it. Okay, and then this will be the maximum extension that got produced in the spring. Okay, so in this situation, obviously the spring force will be greater. So in this situation, spring force will be greater than mg, but here you will still have this mg, right? So here you still got this mg. Okay, so when you look at this situation, it should be clear. mg was acting downwards, fs is greater than mg, therefore it will pull it upwards. Okay, so once this maximum extension has produced, again it will pull upwards and there will be like up and down oscillation. Fine, so you should be clear with this stuff that I've drawn over here. Initially it was like unstretched. Once I release it, it will just fall downwards, it will gain the kinetic energy. Okay, so there will come a point where the spring force and then the mg will balance each other, but that's not going to stop over there because you have kinetic energy into it. Because of that kinetic energy, it will again move against the spring force and it will produce extra more extension to it. So they are asking us to find the maximum extension in this case. They're not asking us to find the mean position where it will come to rest. Okay, so there will be a kind of up and down oscillation and there will come a point where this entire energy will get dissipated to the surrounding in the form of heat or any other form. So after that it will get dampened and it will come to its mean position. They're not asking us to find the mean position. What they're asking us to find is actually the extension, maximum extension. Okay, so to get this maximum extension, what I'll have to do is I'll have to do the energy balance. Okay, so here in this situation, there was this earth surface, right? So you have got the earth surface, and this mass was actually this mass was placed over here, right? So we are moving against the earth's gravitational field, and then the mass was at this position. Then what happened is this mass actually moved downwards and lost its potential energy. Got it? So whatever potential energy it lost, all those potential energy will be stored into the spring. So now I'll be able to equate between the potential energy lost when it moved downwards. Okay, so favorable to the direction of the gravity will be stored into the spring in the form of spring potential energy. Okay, so if I do equate these two energies, obviously these two stuff has to be same. Whatever potential energy that got lost with gravity will be stored into the spring in the form of spring potential energy. Therefore these two stuff has to be same. If I do equate these two energies, I'll end up getting the maximum extension produced in the spring, right? So the notion should be clear. So let me do the mathematical part. Okay, so mathematical part is like two steps, you'll get the answer. Fine. So first I'll have to figure out what was the potential energy lost. So that will be equal to mgh. Okay, so that was lost which got stored into it because of the gravitational field. Okay, so whatever energy that got lost will be stored into the spring in the form of potential energy. Okay, so that will be equal to half k x square, right? So that will be equal to half k was the spring constant and the displacement will be like x square. So here I'll have to get this x. So that displacement should be equal, right? So the h and then the x will be same, right? So this idea should be clear. Initially it was unstretched. Okay, then the maximum extension was produced over there. So whatever h it moved downwards, the same amount of extension will be produced in the case of spring. Therefore, h and then the x are going to be same, right? I'll be able to replace this x in terms of h, okay? So as both are just the same thing, whatever h it has moved downwards, same amount of extension will be in the spring. Therefore, x is equal to h. If I just do the solving, you'll end up getting the answer, right? So in the next step, we'll have like mg x, which will be equal to half k x square, okay? So here x will get cancelled out, and then just do the rearrangement, you'll get the answer. So the x over here, the maximum extension that got produced was equal to x will be equal to 2mg divided by k. Okay, so this will be the maximum extension that got produced. So the answer over here is like option 1. Fine. So it will actually oscillate between 2 mgx, that will be the maximum extension. Then again it will just compress the spring and then it will come to fse, it will come to the unstretched condition. Okay, so then there will come a point where it will reach its mean position. So when it has reached its mean position, the spring force given by the spring will be mg. Same way this will be like mg. So this will be the mean position, right? So if you do the force balance, you'll get the mean position. So if you do the energy balance between the potential energy stored against the gravity with the potential energy stored in the spring, you will end up getting the maximum extension. Same way, if you do the force balance, you will get the mean position. So let me do the force balance and I'll tell you what will be the mean position. So if I do the force balance, you will have like spring force that was acting upwards, which will be like kx, that should be equal to mg. Okay, or else you could do it this way. Kx was like plus j cap and then minus mg, which will be equal to 0. That will give you like kx, which is equal to mg. Therefore, the mean position where it will come to rest will be equal to x, that will be equal to mg divided by k. Fine. So the mean position will be like mg divided by k. It will go double the time of this distance, which is like 2 mg divided by k. So that will be the maximum extension produced. Once that position is reached, you will have spring force to be dominating. Therefore, it will oscillate up and down, right? So you should be clear of this question. So the answer here is like 2 mg divided by k, which is like option 1, right? So this is a kind of logic based question. Okay, so this is a kind of new pattern sum. Fine. So to solve this sum, what I have to do is I'll have to do the energy balance between the potential energy with the case of the Earth's gravitational pull, which will be equal to that of the potential energy stored in the spring. Okay, so these two stuff has to be equated to get the maximum extension. If they're asking you to find the mean position, then you'll have to do the force balance, right? So that's the intuition and thinking that you need to know to solve this sum, right? You shouldn't have any doubt in this sum. It should be clear. Let's move to the next one. This sum is a simple one. Let me do the solving. You have got the potential energy of a long spring when stretched by 2 centimeters is u. Okay, If the spring is stretched by 8 centimeter, the potential energy stored in it is, okay. So here you have got, for the initial situation, I just stretched it to a distance of 2 centimeter, okay. So for u, it was equal to half, okay, k xy, that was equal to 2 centimeter. So whatever the unit it is, I'm just going to take the ratio, therefore it will get cancelled out. So 2 square. So then what they're asking is to find is potential energy stored in it if it was stretched by 8 centimeters. So u dash is something that I need to find in terms of u, right? If I look at the option, it is clear. So that will be like half k 8 square. Got it? Just do the cancelling stuff, you'll get the answer. So half will get cancelled out, k will get cancelled out, same spring. So you will have like 1 divided by 4. So u dash will be equal to 16 times u. So 16u will be my answer, which is like option 4, right? So this is some is like easy one. Just one step, you get the answer, right? It should be clear. Let's move to the next one. Next is sum is, you have got a mass of 0.5 kg moving with a speed of 1.5 meter per second on a horizontal smooth surface, collides with a nearly weightless spring of force constant k, okay. So here you have got a mass and then it is moving on a horizontal surface. This mass is going to collide against a spring. Fine, so the spring constant over here is like 15 Newton per meter. What they're asking us to find is the maximum compression on the spring would be. So what will be the maximum compression with respect to the spring? That's what I need to get, right? So this is a kind of similar sum that we have seen before. So in that case, you have got like a spring that was hanging and then it was moving with respect to the force due to gravity, and the potential energy lost will be equal to that of the potential energy stored in the spring. So that's how I equated in that question. I mean, like couple of question ahead. In this question, how I'll do is whatever kinetic energy that this mass has will be used to store the same amount of potential energy into the spring, okay. So here also I'll have to do the energy balance, but in this situation energy will be balanced between the kinetic energy of the mass with respect to the energy stored in the spring, okay. So if I do equate those two stuff, obviously only one parameter will be like unknown, that will be like the compression, okay. So that will give you the x, okay. So this is going to hit it and it is going to compress the spring. So now let me do the energy balance between the mass and then the energy stored in the spring, okay. So if I do those two stuff, you'll have like half mv square. This was the total kinetic energy possessed by this mass. All those kinetic energy will be stored into the spring by compression. So that will be equal to half k and the x square. So that will be the compression that got produced in the spring, okay. So if I do equate these two stuff, I'll get the answer, right? So half will get cancelled out, half will get cancelled out. So let me substitute like mass over there, which will be like 0.5. The velocity was equal to 1.5 and then 1.5, that will be equal to, yeah, 50, and then you have got like x square, right? So this 50 will come to the denominator, so that one will come to the denominator, okay. So just do the solving, you'll get the answer. Now let me cancel out this 0.5 and then the 50. So you will have like 0.1 and then you'll have like 10, okay. So the next step we'll get the answer, which is like x square, that will be equal to 1.5 the whole square into 1 divided by 100, that will be like 10 power minus 2, okay. If I take root for it, you will have square root for it, you will have like 1.5 into 10 power minus 1, which will be equal to 0.15 meter. The answer here is like option 1, simple sum, right? You shouldn't have any confusion in this sum, simple sum. Whatever energy that was in the form of kinetic will get stored into the spring in the form of potential. Just do the equation stuff, you'll get the answer, right? It should be clear. Let's move on to the next one. This sum is also same as that of the previous sums that we have seen. So here you have got like when a long spring is stretched by 2 centimeter, its potential energy is U. If the spring is stretched by 10 centimeter, the potential energy stored in it will be, right? So same thinking. So just do the ratios, you'll get the answer. So U will be equal to, for the first case, it will be like half k 2 square. And for the U dash, that is something that I need to get. So U dash will be equal to half k. And then instead of x, I'll substitute like 10 square, okay? Just if I cancel it out, I'll get the answer. So half will get cancelled out, kk will get cancelled out, and then half will give you like 1 by 5, okay? Just rearrange it, you'll get the answer. So u dash will be equal to 25u. The answer here is option 4. It should be clear. Let's move to the next one. This question is also easy one. Let me read the question. Here you have got two springs, capital A and capital B, having spring constants Ka and Kb, okay, such that Ka equals to Kb, are stretched by applying force of equal magnitude. Fine. So in those two situations, I'm just going to stretch it by giving a same amount of force, which means you'll have like different displacement, but the force was like same, right? If energy stored in the spring A is like EA, the energy stored in B will be. So I'll have to get the relation. So obviously, with this case, the formula that I have to use is like half. Here, they are just giving the same amount of force, which means I'll have to use this relation Fs square divided by K. Okay, so this is the relation that I need to use, right? So let me take the ratio, you'll get the answer. Fine. So we will have EA, which will be equal to half Fs square divided by Ka divided by, then you'll have the EB. That's what I need to find, right? So EB will be equal to half Fs square divided by Kb. Okay. If I just do the rearrangement, I'll get the answer. Half will get cancelled out. Fs square will get cancelled out. Okay. So what they've given over here is EA divided by EB, which will be equal to KB divided by KA. Okay, for KB, let me substitute like K for KA. I'll substitute like 2 KB. Therefore, you'll have KB divided by 2 KB. Those stuff will get cancelled out. And then you're just left with half. So what they're asking us to find is actually EB. So EB, energy stored in the spring B, will be equal to 2 times the energy stored in the spring A. Therefore, the answer over here is like option 1. Same easy sum. Only thing is you'll have to use a different potential energy formula over here, right? It should be clear. Let's move on to the next one. The next question is, you have got a body of mass 1 kg which is thrown upwards with a velocity of 20 meter per second, okay? So I'm just throwing the body upwards with the speed of 20 meter per second. So that was the initial velocity of fine. It momentarily comes to rest after attaining a height of 18 meter. So once it has reached the 18 meter, it comes to rest. The final velocity becomes 0 at the height of 18 meter, right? How much energy is lost due to air friction? So what they're asking us to find is how much energy has lost to the surrounding because of the air drag force. Obviously, this air drag force is non-conservative force. So whatever energy that got dissipated to the surrounding will never be regained back. Okay. So if there wasn't any drag force, obviously it should have reached more height than this 18 meter, right? So some part of energy has lost to the surrounding because of air drag force. What they're asking us to find is this energy that got lost to the surrounding, right? So now to get the energy lost to the surrounding, what I'll have to do is I'll have to find the difference between the kinetic energy that I gave to that ball, which will be equal to half mu square, right? And I'll have to subtract this one from the potential energy that got stored because of the gravitational field, which will be like minus mgh. If it was like idealized situation, then this half mu square and mgh has to be same, okay? And then it will give you the answer to be like 0 because whatever kinetic energy that I gave should be stored in terms of potential. But in the situation, it is pretty obvious some part of the energy has lost to the surrounding. Therefore, this mgh will be less when compared to this half mu square. So that difference is the amount of energy that got lost to the surrounding, right? Basic, simple understanding, right? Let me do the solving. So you will have half for m. Let me substitute like 1 kg. And then you have got like 20 into 20 minus 1 kg. And then you will have like 10. And the height over here is like 18 meters. Okay. In this case, I'll get the energy loss to the surrounding, or energy lost because of the air friction. Now let me cancel this 2 and then the 20. You'll have like 100. You'll have like 10. So that will give you like 200 minus 180. Okay, so it is obvious 20 joule of energy has been lost to the surrounding. So energy loss was like 20 joule. The answer over here is like option 4, right? It should be clear and it should be easy, right? Whatever kinetic energy that I gave wasn't converted to the potential energy because of the gravitational force field. Instead, some energy got lost to the surrounding due to the air drag force, right? Just do the difference, you'll end up getting that energy loss. Fine, easy sum. Let's move to the next one. This question is also simpler one. Let us do it. You have got 300 joules of work is done in sliding a 2 kg block up an inclined plane of height 10 meters. Fine. So they have given us the vertical height over here, which is like 10 meter. And then I'm just giving a work of 300 joule to slide it up against this inclined plane. Fine. Work done against the friction is. So what they're asking us to find is how much work that I did it extra so that I was able to move that block to a height of 10 meters. That's what I need to get, right? So first what I need to determine over here is what will be the idealized energy that is needed to make this block to move it to a height of 10 meters. Okay, so it's a kind of situation where if there wasn't any friction, what will be the energy that was actually needed. So here they have just clearly given, I have given like 300 joules. So the subtraction will give you what was the extra work that I gave so that I can overcome the friction. Fine. So the logic should be clear. So let me draw the diagram, you'll get it. So you have got an inclined plane, got it, and then you have got a block at this instant, at this bottom position. So the height over here is like 10 meters. So the height over here is like 10 meters. So I'll have to move this block to a height of 10 meters. Got it? So if I have to move this block to a height of 10 meter, what should be the energy that I need to give if there wasn't any friction? That's what first I need to get it. So that will be equal to mgh. So whatever potential energy that is going to get stored will be the energy that I need to give, right? So which will be equal to, mass is like 2 kg, and then acceleration due to gravity is like 10, and then the height was equal to, vertical height was equal to 10. Therefore the energy that actually needed over here is 200 joule. Okay, but I just gave like 300 joules of work, which means I just gave 100 joule extra work to it, right? So 300 joule was like an extra work that I gave to it instead of 200 joules. Then what will happen to that 100 joule? That 100 joule is something that I gave so that I can overcome the frictional loss in that case, right? So to overcome that friction, I just gave extra 100 joule of energy to it, right? So that's what they're asking us to find. What was the work done against the friction, which means friction force is actually opposing me. So there is a heat loss in the surface. So that heat loss will be equal to the 100 joule. That's the extra amount of energy that I gave to that block. Okay. So the answer here is obviously 300 minus 200, which will be like 100 joule, right? It should be clear. Simple sum. Let's move on to the next one, which will be the last one for this session. This sum will be based on the concept of power that we have learned. Here you have got a body of mass 1 kg begins to move under the action of a time dependent force. They have given you some equation, some vector related to the force. So there is a body which is like 1 kg and it is going to move under the action of force. Okay, so the force, so they have given you the vector for that particular force where I cap and j cap are unit vectors along the x and y axis, obviously. What I need to find here is what power will be developed by the force at time t. Okay, so first let me figure out what should be the formula that I need to use. So here you have got power. What is the formula for the power? It will be like dw divided by dt, right? Here if I have to solve this one, so obviously dw will be equal to vector f dot dx, right, divided by dt, right? That's how it has to be, right? So what will be like dx divided by dt, dx divided by dt, or dr, depending on the x and y component. If it was only along the x, it will be like dx, or else I'll put it this way, dr divided by dt, right? So what should be like dr divided by dt? That is nothing but the length covered divided by the time interval will be the velocity, right? Therefore, there is like another one formula for the power, which is like extra step to it, that will be vector f dot vector v. So this one will also give you the answer for power. Okay, so now I'll be able to use this formula so that I can plug in the data that they've given in the question. So here they have given us the vector f which I'll be able to put it straight away into the vector f over here. And then vector v is something that I need to get. So to get the vector v, what I could actually do is they have given you the force, okay? So force is nothing but the mass times the acceleration. From that, I'll be able to get the acceleration. So acceleration is nothing but the differentiation of the velocity with respect to time. So if I just able to integrate it, I'll end up getting the velocity over there. Okay, so if I get the velocity, then obviously I will be able to get the power. Okay, just the dot product of vector f and vector v will give you the power, right? So to get the velocity vector, let me first take the force. So force over here is vector f was equal to, it was equal to 2t I cap plus 3t square j cap. Okay, so this term has to be equal to the force, which is nothing but the mass times acceleration, vector a, right? From the question, it is clear the mass was equal to 1 kg. Therefore, here I'll have to just substitute 1. So vector a will be equal to the same entire term. Okay, so you will have vector a, which will be equal to this complete term. So what will be the vector a? It will be equal to d vector v divided by dt. So that will give you the vector a. So to get the velocity vector, obviously I'll have to do the integration of a dt, right? So vector, okay, yeah, final velocity vector v will be equal to vector a dt. Okay, so just do the integration, you'll end up getting the velocity v. Fine. So here in this situation, they have just given us clearly it starts to move under the action of time dependent force. So it begins to move because of this force only. Therefore, initially the velocity of that body is going to be 0. Therefore, I do not want to worry about that initial velocity which should be there in the body, okay? Because it only starts to move because of this force. Therefore, initially it was at rest. Got it? Therefore, vector v, if I do the integration, I'll end up getting the velocity vector that is needed over here. Fine. So to do the integration, I'll just have to substitute the vector a that was given in the question. So here velocity v will be equal to, vector v will be equal to integral of a dt, that will be like 2t I cap plus 3t square j cap dt. Okay. Now if I do the integration, you'll end up getting the velocity vector. So here you will have 2t square divided by 2 I cap, and then you will have like 3t square divided by 3t cube, right? N plus 1, so that will be like t cube divided by 3 j cap. Okay, yeah, so here I have done indefinite integral, which means I do not want to substitute limit over here. Okay, this is because initially I've told you because of this force field only it is going to get the velocity, okay, which means initially it was at rest. Fine. So whatever time that you are going to plug in, so if you're just going to plug in like 2 into this equation, then you'll get the velocity when the time interval was equal to 2. Okay, you'll get that particular velocity vector. Fine. And by the way, initially also there wasn't any velocity into it. Therefore that initial, so whenever you do an integration, you'll end up adding a constant into it. So here initial velocity was 0, therefore you wouldn't have any constant into it, right? So while doing like math sums, you will just add constant to it when you do the integration. So that constant will be the initial condition. So here in this situation, it is pretty obvious. Initially, there wasn't any velocity into it. So you will not have any constant into it. So just if you just plug in the time that is needed, you will end up getting the velocity at that particular time. Okay, so as the initial velocity was 0, I do not want to worry about the constant which we will generally put if you do the integration. Okay, fine. So this step has to be clear. So that is why it is called as indefinite integral, which means whatever value that you plug in, you end up getting particular answer for that particular value. Okay, so here that will be the velocity at that particular time, right? So now I have found out the velocity vector. So the only part that is missing is the power. So the formula for the power is actually vector f dot vector v, isn't it? So here the answer will be like vector f is same as that of the acceleration because mass is equal to 1. So so the force will be like 2t I cap plus 3 t square j cap. Okay, so now I have got the force. I'll have to do it dot product with the vector v. So that will be like, so let me cancel out this one. T 2 2 will get cancelled out. 3 3 will get cancelled out. So you will have like t square I cap plus t cube j cap. If I just do the dot product, I'll find the final answer, isn't it? Yes. Just let me do one more step to it. I'll get the answer. So the next step will be, as it is dot product, I'll have to multiply I with I and then j with j. Okay, so the first one will be like 2t cube and the next one will be like plus 3t power 5. So the power for this particular force field they have given us 2t cube plus 3t power 5. So 2t cube plus 3t power 5, which is like option 2. Fine. So the answer here is like option 2. Okay. So you should be clear with this sum. So in this sum, only tricky part is I'll have to use a new formula for the power, which is like vector f dot vector v. So I just found it just by adding like one extra step to the dw by dt. I just got that formula, which is like vector f dot vector v. You should be clear with that formula because we will use this formula most often in the upcoming chapter. So that formula has to be clear. Then they have given you the force field. From that force vector, what I need to get is actually the acceleration, right? So to get the acceleration, mass was equal to 1, therefore I got the acceleration straight away. So from that acceleration, I'll have to find the velocity. So to get the velocity vector, I just have to integrate that acceleration with dt. So when you do the integration, obviously whenever you do the integration, you add constant to it. So, okay, so that's a math logic which you need to know. But in the situation, I do not want to add that constant because in the initial condition when time was equal to 0, the velocity was equal to 0, right? So now just by plugging in the time into the velocity vector, I'll be able to get the velocity at different time interval. Okay, so that stuff is done. So this is called as indefinite integral because I do not put in the limits over there. Okay, so that's a kind of indefinite integral, which means whatever time that you give, you'll get the velocity vector for it. Now I have found the velocity vector, then I'll have to get the power. So to get the power, just do the dot product between vector f and then the vector v, you will end up getting the power. So you've got like little more extra steps to solve, but it should be clear, right? You shouldn't have any doubt in this sums that we have solved. Okay, so in this session, we have seen sums that are related to power, and then we did see one or two sums that are related to vertical circular motion of a bob, and then we did see sums mainly related to spring. Okay, you should be clear with all those concepts. Fine, you shouldn't have any doubt in the sums that we have seen. So we have seen around like 10 sums in this session. You should be clear with all the 10 sums that we have seen. Fine. So this the video gets completed. Bye.